Okay, so welcome back to another video. Here we have a little number theory problem that's very similar to the inequality problem that I posted a couple videos back with that integral and summations, but this is a little bit different. This is that we want to find a natural number m such that 21 to the power m is strictly less than 7 to the power 110, which is less than 21 to the power m plus 7. So from the previous video I did similar to this, that was within the center of finding a bound that satisfied the inequality. Here, in this case, we're looking at a good bound, finding a natural number m that satisfies the bound that is in between our the inequality with holding that 7 is to the power 110 is in between the two. So this is just a pretty straightforward number theory problem. You can just use the idea of using your rules of, with exponents and, of course, with the base itself. That's how we're going to start off this video, but it's just by analyzing just the base itself, or well, from the center of this inequality specifically. Utilize that, then make a bit of a comparison using that inequality to form a little bound, and then utilize that bound to help find our natural number m satisfying this inequality. So I don't have anything else to add, so let's just jump in. So you want to notice that 7 to the power 110, we can write that as a form of a division of 21 to the power 110, then divided by 3 to the power 110. Obviously, this still satisfies the rules with exponents, so this is just 21 divided by 3 as a base, which is still 7, and then they share the exponent, so that's why we can write it in this form. So let's actually notice that for the following. We know that 3 to the power 10 is equal to 59,049, and then 3 to the power 11 is equal to 147. And here we want to create this little bound, and we can say that here's something to know. We know that another thing to put down is that 21 to the power 3 is actually just equal to 9,261, and then for 21 to the power 4, that's equal to 194, then 481, 194,481. Okay, so from there we can actually form this little inequality and say that 21 to the power 3 is strictly less than 3 to the power 10, which is strictly less than 3 to the power 11, strictly less than 21 to the 4th power. From there, we can actually do a little bit of utilization and really multiplication from our two bounds, or not two bounds, from all throughout this entire compound inequality. Specifically, we're going to look at it in two ways. So we're going to look at these two terms, and then these two terms will inform the inequality, of course. So what we can do for 21 to the power 3, so I'll start with this inequality, 3 to the power 10, we can multiply by 11. So if we multiply 11 to the exponents, so I'll just write exp, we can write this 21 to the power 3 times 11, strictly less than 3 to the power 10 times 11. Okay, then we know that from there, this is just 21 to the power 33, strictly less than 3 to the power 110. Okay, so doing the same thing over here, 3 to the power 11, strictly less than 21 to the power 4. What we can do from here is I'll multiply 10 to the exponents. Then from there we see that we have 3 to the power 11 multiplied by 10, strictly less than 21 to the power 4 times 10. Then from there we see that we have 3 to the power 110, strictly less than 21 to the power 40. Okay, they share the same numbers over here, so we can actually set a little compound inequality with the bounds we just formed. So 21 to the power 33 is strictly less than 3 to the power 110, strictly less than 21 to the power 40. Okay, so that's a good establishment that we have reached. So what are we supposed to do from here? Well, it's actually just very simple. We can just take what we started earlier. We said that 7 to the power 110 is equal to 21 to the power 110, then divided by 3 to the power 110. We'll start from the 21 base that we just, showed or rather we use the fact from, the multiplication from there and the exponents too, and we could just use this top numerator and divide everything from all the from our inequality over here. So what this also means is that because we have, with with the exponents larger than the other, then that means doing with this whole utilization with inequalities, you would have to switch the signs. Obviously, when you have a bigger denominator than the other, then that means, the other is going to be smaller in terms of that. Okay. So from there we have 21 to the power 110. We divide this by 21 to the power 40. Then, of course, switch the sign because we have a larger number than the others, so that switches. So we have 21, then divided by 10 to the 0, then divided by 3 to the power 10, 110, excuse me. And then strictly less than 21 to the power 110 divided by 21 to the power 33, okay? Then we notice that if we just use the rules of exponents, we could actually form the subtraction with the exponent. So the left side of the inequality will get 21 to the power, so 110 minus 40 is 70. Then we just showed that 21 to the 110 and 3 divided by 3 to the 110, that's the same thing as 7 to the power 110. Then the last part is just do the subtraction over here, 110, 33, so that will be 21 to the power 77. But hence we have that we want to show that find an m such a satisfied inequality. So m and then m plus 7. So if you actually just look between the left hand side and the extreme right hand side of the inequality, we can see that we have just found our natural number m forming this bound. So hence m in this case is actually just equal to 70, and therefore we are done like that, just like that. So there it is. This is very not too convoluted, not too crazy. This is just this is a very simple number theory, just utilizing everything you know about exponents and with the bases. Also, it's also neat to see that if you were to take the natural log of the if you take the natural log of base 21 of 7 to the 110 power, you'll get an approximation, a decimal approximation that is close to 70. I forgot the number, but I'll actually just put that down in in the video just to give you the exact number. So yeah, that's pretty cool if you ask me.